Hello, and welcome to Astronomy 100. In previous segments, we've been talking about the nature of light and how light can tell us information about the objects that we study. The light comes from these objects, travels great distances across the universe, and the light itself can contain the important information about the object that is producing the light. Now, when it comes to studying our universe, astronomers are interested in many things about the objects that we study. But there are two important concepts that stand out, two things that we would like to measure about the objects that really stand out amongst many of the other things we could possibly learn. For instance, astronomers, when we study the objects of our universe, we are interested in knowing the temperature of the objects that we study. A couple of examples are, we can see the sun with our telescopes, but we would like to know the temperature of the sun without having the need or the means to go to the sun to be able to measure it in a traditional fashion. We would like to know the temperature of this region of space. Obviously, there's a lot going on in this region of space, but we would like to know the temperature of this part of space. In this picture here of Jupiter, Jupiter has many different layers of clouds, and of course we would like to know the temperature of the clouds of Jupiter. So what all three of these have in common is the inability for us to go to these places to measure temperature in the traditional fashion, such as dipping a thermometer into these places to know the temperature. The other thing that we would like to know is we would like to know what these objects of our universe are made out of, or the chemical composition of our universe. For instance, the sun is made up of many different types of things, but we would like to know what the sun is made out of. The problem is that to know what the sun is made out of in a traditional sense, we would have to go to the sun and gather some of its material to figure out what it's made out of. Obviously, this is some sort of material. We would like to know what that material is. Jupiter's clouds are made out of some sort of material. We would like to know what that is. So we'd like to know the composition of things in our universe, but we don't have the means to go to these places to gather samples. So what we're going to do today is we're going to focus on the first one. And if you remember, we had two goals. And the first goal is, how do we know the temperature of something, of the universe, an object of the universe, without having the ability to touch the object? And what you may, of course, remember is that any time in your life when you measure the temperature of something, you're probably coming into contact with the thing it is that you're measuring when it comes to its temperature. An example may be that when you were young and you were running a fever, your mother probably put her hand on your forehead, and by feeling your forehead, she could feel at least get an idea of what your temperature is by coming into contact with you. But obviously in astronomy, we don't have this luxury. We don't come into contact with these objects that are very far away. So we need to determine the temperature of something without the ability to touch the object. So here are the key concepts. The first key concept is we need to know what is temperature. So what is the definition of the concept of temperature? And then related to that is we want to know, how do we quantify temperature? In other words, how do we attach a number to the temperature that we're measuring? You can't simply say things like hot and cold. Hot or cold is a relative term. It's hot compared to something else, or cold compared to something else. So what we actually need is a number that represents the concept of temperature. So let's start with the first one. The first idea is, how can we define the concept of temperature? How can we relate it to what we see? So we want to make this connection between electromagnetic radiation, which, if you recall, is light, and temperature. So let's start with our definition. One of the most important definitions of the entire astronomy course is the definition of temperature. By definition, temperature is simply a measure of the average velocity of atoms or molecules. What's important to understand is what this means is temperature is actually measuring movement. When you measure the temperature of something, you are measuring the inherent movement of the atoms or molecules that make up the object that you're measuring. So temperature is a measure of how atoms and molecules will move. Now, a couple of ideas that go with this is the idea that everything in our universe has a temperature. There is no place in our universe that is without temperature. The only real exception to this might be a black hole. A black hole is an object that has no temperature. In fact, the concept of temperature doesn't even apply to a black hole, but we'll talk about that at a later date. So everything in the universe has a temperature associated with it. So the idea is, how do we actually quantify temperature? How do we attach a number to the concept of temperature? So what I'm going to do is start off with a brief video that will give you the idea of what we mean when we define temperature as the movement of atoms or molecules that make up a particular substance. So in this video, what I'm going to show you is an imaginary box. This is a two-dimensional box, meaning that the objects in the box can move left and right, they can move top to bottom, but there is no coming out of the box or going into the box. And so what I want you to notice is the little spheres. Each of these spheres is to represent an atom, and each of these atoms has the ability to move left and right, top to bottom. What I'm going to do is I'm going to start off by playing the video, and you're going to notice that the atoms are zipping around. So let's go ahead and get that going here. The atoms are moving, running into each other, running into the walls of the box. Notice they're not all traveling at the same speed. Some are fast, some are slow. But when I change the temperature of the box by sliding the bar on the bottom, you'll notice that on average they're moving faster. Some of them are still slow, some of them are faster than they were before, but on average the collection of atoms is moving faster or a higher temperature. When I reduce the temperature of the box by sliding the bar to the left, I'm actually slowing down the atoms or molecules, and that's of course making them appear collectively slower. So on average, they're moving slower, even though some are still slightly faster and some are still slightly slower than the collection. So temperature inside of this, the temperature inside of this box, is the average velocity of all of the atoms or molecules that make up the material inside of this box. So again, temperature is movement. It's the internal energy of the atoms that create the movement of those atoms. Now, the idea of how do we attach a number to the concept of temperature gets a little bit more tricky, but let's go to a picture where I'll show you how to understand how this works. To understand how attaching a number or quantifying temperature works, we have to first understand that in our universe, various materials can come in a variety of different phases. We call this the phases of matter. You're probably familiar with the term the solid phase, the liquid phase, or the gaseous phase. These vertical lines represent changes from one phase to another. So liquids can become gases, solids can become liquids, but it also works the other way around. Gases can become liquids, and liquids can become solids. Now, when you move from left to right on this illustration, what you're actually seeing is a temperature change. So when I start on the left and work my way to the right, the temperature is increasing. Notice the arrow pointing from left to right. So as I go from left through the middle to the right, think of it as the temperature of the material is increasing. Again, these vertical lines represent a change from one phase to the next. So we're going to label those phase change. Solid becoming a liquid, liquid becoming a gas. There's some terminology that you're probably familiar with. For instance, when we have solids become liquids, that is when something melts. Melting is a solid becoming a liquid. And when a liquid becomes a solid, you're familiar with the term freezing. So any liquid that becomes a solid is in the act of freezing. Likewise, anytime a liquid becomes a gas, that process is called evaporation. And anytime a gas becomes a liquid, that is called condensation. So evaporation is a phase change, condensation is a phase change, etc. Now, to fully understand what it means for something to be a solid or a liquid or a gas based on temperature, I'm going to introduce a collection of atoms. It's a little bit tough to see, but if you look very carefully, you'll notice that these atoms here have little lines that are connecting them together. The idea is that every atom has the ability to bind with its neighbor, and there's a force that binds the atoms to its neighbor. So each of these white lines represents a force of binding energy that binds the atoms together. So this atom is bound to this atom and this atom nearby, as well as this one and this one. Now, these forces that allow atoms to bind together have a certain strength. if you have an opposing force that is stronger than these binding forces, these forces can be broken. If you don't have a force that is as strong as these binding forces, these binding forces stay together. So in a solid, the atoms are bound together with these forces and they're locked into place. But what's critical to know is that the atoms in a solid are actually still moving. In a solid, the atoms are vibrating. So they're vibrating with energy, but they're vibrating in place. The problem is that the energy of their vibration is not enough to break the binding forces that hold them together. So they stay together as a solid, stay together locked in place as a solid form, as we're familiar with. But if we move from left to right, what you'll notice is the temperature is going to rise. And at some point, the vibration of these atoms becomes much more vigorous because remember, temperature is movement. If the temperature goes up, the vibration of the atoms increases, and the vibration increases to a point where the movement of the atoms is too much for these binding forces to hold them together. And so what will happen is the atoms now vibrate with energy but can't bind themselves to each other to lock themselves into the solid form. So we now have a liquid. So you notice that they're now the collection is together, they're moving in a way that they're vibrating, but they're still together as a group, just not able to stay as a solid. If the temperature of the liquid increases, eventually the vibrational movement of these atoms becomes so severe that the atoms can now move in a way where they break free from the collection. And so the atoms can now zip around in 3 dimensions, they can bang into each other, they can bounce into walls, and we have a gas. So a gas is atoms that are freely moving with enough energy that they can move around free from any sort of a collection. So as we change the temperature of the material, it goes from a solid to a liquid to a gas as the movement of the atoms increases. But don't forget, if we lower the temperature, it will then go from a gas to a liquid and a liquid to a solid. So how do we attach a number to this concept of temperature? Well, the way that we do this is we come up with a numbering system that is related to the movements of the atoms and molecules. And traditionally, what was used is the substance of water. Water is something that's all around us, so water seemed something that would be very useful. And you'll notice that the numbering system that we use, called the centigrade scale, attaches the number 0 for the phase change where water goes from a solid to a liquid, in other words, where water melts, or from a liquid to a solid where it freezes, or 100 represents the phase change where water goes from a liquid to a gas or evaporates. Well, in the United States we don't use the centigrade system, so we instead use a system called the Fahrenheit scale. It still uses the concept of water, but the numbers are a little bit different. For instance, the phase change where water goes from a solid to a liquid is assigned the number 32, and where water goes from a liquid to a gas is assigned the number 212. So you'll often hear that the boiling point of water is 212 Fahrenheit, which means water will go from a liquid to a gas. So here is 2 different ways to attach a number to the concept of temperature. The problem is in the United States we use the Fahrenheit scale, the rest of the world uses the centigrade scale. So how do we solve this problem? Well, unfortunately, we have to convert between the two. If you live in the United States and somebody tells you a temperature centigrade, here's how you convert it to Fahrenheit. If you live somewhere else around the world and somebody uses a temperature Fahrenheit, here's how you turn it into centigrade. So this very complicated conversion poses a problem. Well, scientists have a solution to this. What we do in science is we don't use either system. Instead, we use a system that is related to the concept of temperature, not related to the concept of the temperature of water, but related to the very physics of what temperature actually means. And when we get together in the next segment, I'll show you how we use this system to define temperature quantitatively in a way that can be universal, that everybody can use. I hope you'll join me.